Remainders are flawed for the uniform gauge, yet they're on Euclid built our common stage. Our prime roots shape what we become, irreducible truths that time can't overcome. We embrace classes not congruent to our trace. We dwell with our inverse face to face. When power surge and all seems gone, faith ma points us back to one.
Previously, we introduced the concept of modular arithmetic, where addition, subtraction, and multiplication can be defined in a manner analogous to arithmetic with integers. However, when it comes to division, things become trickier. Recall that for two integers p and q, where q is not 0, dividing p by q can be understood as multiplying p by the inverse of q. Once the inverse is defined, so is the division. In modular arithmetic, we adopt a similar approach. Since modular multiplication is defined, division can proceed via multiplication by an inverse, provided that a modular inverse exists. With this motivation in mind, in this section, we define what a modular multiplicative inverse is and study its existence and uniqueness. Let a be an integer and n a positive natural number. If an integer x satisfies that ax is congruent to 1 modulo n, we say that x is congruent to the inverse of a modulo n, or simply, x is the modular inverse of a mod n. Let us look at some examples. Example 1, 2 times 4 equals 8, which is congruent to 1 mod 7. So, 4 is the modular inverse of 2 mod 7. Similarly, 2 is the modular inverse of 4 mod 7. Example 2, 3 times 3 equals 9, which is congruent to 1 mod 8, so 3 is the inverse of itself mod 8. Example 3, 2 has no inverse mod 4. This is because for any integer x, 2x minus 1 is always an odd number, which is never divisible by 4. Hence 2x and 1 can never be congruent mod 4. A few remarks might be helpful at this stage. First, the modular multiplicative inverses always show up in pairs. As the first example reveals, 2 and 4 are inverses to each other mod 7. Second, sometimes an integer can be its own inverse, as the second example suggests. Finally, the third example indicates that some elements might not have a multiplicative inverse at all, and hence brings us to a fundamental question. When does a modular inverse exist? And if they do exist, are they unique? Here is our main result on the existence and uniqueness about the modular multiplicative inverses. Let a be an integer and n a positive natural number. The modular multiplicative inverse of a modulo n exists if and only if a and n are coprime. Moreover, if a modular inverse of a modulo n exists, then it is unique modulo n. That is, if two integers x and y are both inverses for a mod n, then x and y must be congruent mod n. We start by proving the necessary and sufficient condition for the existence of an inverse. Assume that an integer x serves as the inverse of a, that is, ax is congruent to 1 mod n. By definition, it follows that n divides ax minus 1. Which is logically equivalent to saying that ax minus 1 equals ny for some integer y. After rearranging the terms, we see ax plus n negative y equals 1. In other words, x and negative y form a solution to the linear Diophantine equation, a alpha plus n beta equals 1. By Bézout's identity, this is equivalent to the coprimality of a and n. Next we turn to the uniqueness. Given two integers, x, y, such that ax is congruent to 1 mod n, if x and y are congruent mod n, then multiplying a on both hand sides shows that ax is congruent to ay mod n, which is in turn congruent to 1 mod n. Thus y is also an inverse of a. Conversely, if ay is congruent to 1 mod n, multiplying y to both sides of the first equation leads to yax and y being congruent mod n. However, since y is also an inverse of a mod n, the left-hand side is congruent to x mod n, we conclude that x is congruent to y mod n, and hence the uniqueness. With this main result in hand, we proceed to the case where p is a prime number. Consider any integer a that is not divisible by p. Since p is prime, a must be coprime to p, thus the inverse of a modulo p exists, as is guaranteed by the previous theorem. Applying the above results to the least residue system modulo p, we obtain that each non-zero number in this least residue system has a unique multiplicative inverse in the same set, which is non-zero as well. To see this, let a be a natural number between 1 and p minus 1. Since p is prime, a is not divisible by p. Thus, there exists some integer x, which is an inverse of a mod p. Since the least residue system is complete, there exists a unique number b in the least residue system, which is congruent to x, and hence is also an inverse of a mod p. Clearly b is non-zero, and we have achieved the desired result. To finish this section, let us study a concrete example by taking p equals 7, and consider the set consisting of 1, 2, 3, 4, 5, and 6. Direct computation shows that 1 and 6 are each their own inverse mod 7. On the other hand, 2 and 4 are inverses of each other mod 7. Similarly, 3 and 5 are inverses of each other mod 7. We see that each number in this set has a unique inverse in the same set. Moreover, the head 1 and the tail 6 are inverses of itself, and all the body terms form two pairs of inverses. Keep this observation in mind, which will be the key idea for the proof of Wilson's theorem, which we will discuss in the next section.
新了，ten say。